Hello everyone! Today's webinar will begin in just a moment. So thank you everyone for joining in today. Today's webinar is going to be on RF receiver design. If you're interested in finding out about any of the other free webinars that we'll be running or downloading any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy, where you'll find everything there. So before we get started, I'd just like everyone to know that this webinar will be recorded and you will be receiving a recording of it in a few days. So you can go ahead and share it with anyone you'd like to or rewatch it. And if during the webinar you have any questions, make sure that you ask them in the chat section on the right side of the menu, and we'll be sure to get to all those questions as we get to the end of the presentation. So I'm pleased to introduce Neil Jarvis today. Neil is an RF applications engineer known for his expertise in RF and microwave design, specializing in vector network analysis and spectrum analysis. In his 25 plus years experience in design engineering, test engineering, product development, Neil has held positions at National Semiconductor, Teijin Corporation, Northrop Grumman Corporation, as well as Agilent Technologies. In addition to his degrees in math, EE, technology management, and systems analysis, Neil holds several patents in RF technology. For more on Neil, you can go ahead and check out his LinkedIn page at linkedin.com/in/Neil R.K. Jarvis. And now, without further ado, I'm going to hand it over to Neil. Neil?
Thank you very much. So we're going to be talking about RF receiver design. And if you had attended some of my previous sessions, I've talked to some broader topics, and I'm really trying to break up the process. And you'll see as we move forward some of the technologies I'm going to talk about. Here's a copy of my card. I work for Rohde & Schwartz Corporation. I'm an applications engineer in the Bay Area, and I've been working in microwave and RF for many years, in a variety of different areas. So I'm going to start out with a little bit of a review of previous topics I've spoken about. And so looking at this slide, you'll see that this is sort of a simplified diagram indicating the steps in the communication system process. So if you look at the top left-hand corner, you see there's some sort of information source, and the simplest case originally was really voice, people speaking to each other over wireless or wire. Obviously, it started out over wire. So you take the information source, and you have to take that information, put it into some type of structure that you can transmit over a medium. Then it's transmitted over that medium, goes through the medium, it's received on the other side. Then you have to take that transmission protocol out of it and then take the data or voice, whatever it is that you want to listen to on the other end. Obviously today more things are geared around data than voice. Voice is actually even data now. So I've spoken in the past on the on the overall diagram and the transmission medium. Today I'm going to talk about the receiver. Future broadcasts will be talking about transmitters and other things. So you'll see here we're focusing on the receiver. Okay, so I'm going to review a little bit from the previous presentations that I gave. So real quick, we're talking about RF and microwave. So typically the propagation of the information is going to be over free space. So I'm not talking about over fiber or cable, although those are certainly valid mediums for transmission, but that's not what we're talking about today. So overall, you'll be sending data or information from a transmitter through an antenna, propagating through free space, then received on the other end with another antenna and processed through a receiver. This process of propagation through free space will be taking advantage of mathematical formula, which is called the Friss's equation, and kind of simply put, it's really if you took an antenna and for the most part, things will start out propagating isotropically, in other words, like a sphere. So it'll go equally in all directions, and it'll be governed by this mathematical equation. At previous slides, I had spoken about dBs and dB math. So this is the kind of common nomenclature we'll speak about in RF and microwave design. And this equation here, A equals 32.4 plus 20 log V plus 20 log F, is really the key equation that governs the propagation over free space. Okay, so modulation. So the key thing is the propagation over free space. Really, you're going to determine what frequencies and things you're going to use based on the characteristics of the area or where it is you want to propagate this information. It could be to a satellite up in orbit. It could be in a city. It could be in a rural environment. And all of these different areas or places where we do these things have somewhat different characteristics. So what frequencies and things we use will determine what we use. But the key thing is, taking that information, you have to put it on that signal, which we call a carrier, and that carrier really is the thing that propagates through free space. So in cell phone technology, that's typically around a gigahertz, and you probably have seen in wireless communications things like 802.11, Wi-Fi, things like that. Things are transmitted over 2.45 gigahertz. But the key thing is that we need to get the information on that frequency so that we'll modulate that carrier, i.e. adding information or modifying the characteristics of that carrier. Then on the other end, we're going to demodulate it or remove that information so that we can further process it. Okay, so real quick, how's this done? Well, if you look at an analog sine wave or analog signal that's going to be propagated through free space, it has a given amplitude, a frequency, and a phase. So in order to propagate these signals through free space, or in order to add information to these signals, we'll modify one of those characteristics. So you see there that equation A sine omega t plus phi. The information will be added onto those variables. So what does it look like? Well, it's the process of varying one or more of these characteristics of the carrier wave. And why do you do it? Well, again, we want to match the transmission characteristics of the medium, depending on where and how. And the transmission efficiency also is a function of the antenna. So you'll see on your cell phone, you might not even see your antenna. It might be a small wire sticking up, or you might see on the side of the road when you go by a military base some huge dishes. These are all different types of antennas that are governed by the characteristics of the frequency or modulation that we're using. Okay, so what does this look like? Well, we take these characteristics. So there's a sine wave, and you can see here on this diagram, you can modify the amplitude, and that's what that looks like. The information's on the amplitude. You can multiply the frequency. You can see it speeds up when I'm adding information. You can multiply or modify the phase, whereby you're changing the phase characteristics at intervals determined by whatever signal you're sending, or it could be some combination of these. Okay, so looking at a receiver, now we're really going to focus on the receiver. Okay, so receiver really consists of an antenna. There's always a filter at the front end, then a low noise amplifier, and typically you're going to take that higher frequency signal, which is typically called the carrier wave, and we're going to take that down to a lower frequency signal so that we can take the information off, i.e. demodulate it, do some signal processing, and then take that information out and do whatever we want with it. Okay, so key thing when you receive signals really is there's noise in the environment. You've all, if you're as old as me, you've turned a dial on your radio and you've heard that hissing noise. That hissing noise is noise from the environment, okay? And it's always there. There's thermal noise, which is really governed just by everything around you, the sun, things like that. Then there's noise from other things out there, people's cell phones, people's garage door openers, things like that. So when we design a system, particularly on the receive side, we need to be aware of these noise, and we need to make sure that we can respond to our desired signals in the presence of noise. And you'll see as a signal is attenuated, i.e. it's reduced in amplitude, it becomes more and more difficult to detect that signal relative to the noise around it. So you'll see an analog used to have that hissing noise, but digital receivers actually have coding put into the signal, so it actually has redundancy built in. So typically you won't have that hissing noise, but you'll have a more steep break-off where you will start having blocks of data where there's no sound at all, for example, on a satellite radio, or you'll just lose your signal altogether. Okay, so this is just showing you a plot from a spectrum analyzer. I work for Rohde & Schwarz again, so we make these, so I have to put some slides in here showing our products. But you'll see here it's showing you some markers in a noise environment. So that you can see here, this is just noise from the overall environment, and it's at a frequency where there aren't spikes. This is just thermal noise, i.e. noise from the sun and everything around you. Okay, so input noise, this is really the key thing that you're going to be focused on. Rarely do you play with signals that are above 100 gigahertz, but this is the kind of standard approximation that people will see. Below 100 gigahertz, the noise is governed by KTB. So that's Boltzmann constant for those of you who've done physics, temperature in Kelvin, and the bandwidth of the system. So really, what you'll hear people typically talk about is KTB, which is minus 174 dBm in a 1 hertz bandwidth. So that's basically telling me that anything at or below that signal, I won't be able to see it because it's the same size as the noise environment around it. So therefore, it's difficult to discern it from the world around it. And there are certain types of receivers that will allow you to maybe go below noise floor with processing gain, but I'm not going to be speaking of those. Also, there's situations where you can use certain cooling mechanisms to reduce that, but again, we won't be talking about that. Okay, so we have this noise in a 1 hertz bandwidth, but typically when you look at a system, you're really going to be looking at a channel bandwidth. So for example, it might be a 10 megahertz channel or a 1 megahertz channel, things like that. And typically these things are governed by a standard. So for example, you probably have heard of a thing called LTE, long-term evolution. So that's kind of what the modern technology is for cell phones. You might have heard of 5G, that's the next generation. You might have heard of 4G or Wi-Fi or all these various different standards which have different characteristics, one of them being the channel bandwidth. Okay, so when you take that bandwidth, in this example I'm giving here, if I had a 1 megahertz channel bandwidth, that tells me the noise floor in that bandwidth of 1 megahertz is at minus 114 dBm. And it's done by taking 10 log of 1 megahertz, giving you 60 dB. So this is 114 dBm in a 1 megahertz bandwidth is the noise floor in that channel. So if you want to demodulate a signal below that, it's going to be challenging, if not impossible. So when we design a system, the key is that when you receive a signal, in an ideal world, if you look at the previous slide, my noise floor is at minus 114 dBm in that 1 megahertz channel. I don't want my system to add any more noise to that. So ideally, I'd be able to pick out a signal slightly above that minus 114 dBm, but perhaps just slightly above it. But the reality is, if you've done engineering, you know that there's no perfect system. So when you put in an amplifier, which is typically near the front end of a system, it's going to add some noise. Anything that's an active device will add some noise. While noise added from kind of more modern technologies is very low. You see receivers that have LNAs in them that might be in tenths of a dB, which is unheard of going back to sort of the 60s or 70s. In fact, I had a colleague I worked with who got his PhD in the 70s designing an LNA that had a noise figure of 12 dB. So by today's standard, that wouldn't be very good. We're now in the tenths of dBs. Okay, so what is noise figure, noise factor? It's a ratio of how much noise is really added by a device, and it's typically going to be an amplifier. Okay, so you see the signal-noise ratio in over the signal-noise ratio out. Okay, so this picture really has a great indication of what this kind of means. And you see here, if I have a small picture, so if I was sending video, you'd see that I have signal-noise ratio in, and that's a very nice, clean-looking picture, and it's small. Well, I want to make that picture bigger. So what do? I put it through an amplifier. Well, if that amplifier is adding noise to it, you can see here that I get some random pixels in the picture, which are now degrading the quality of the picture. So that's really the addition of noise. This isn't necessarily how a real system would work, but I think it gives you a good value in terms of what this all means. So typically you'll hear noise factor, that's talking in linear terms, or noise figure, which is in dB scale. So typically RF microwave engineers talk in dBs. You know, you might find if you're new to this, when you first start playing around with dBs and you take 10 log of some ratio, you'll be going back and forth, but you actually find when you get good at it that you want to just live in the dB world. Because the nice thing for dBs is you actually do everything by adding and subtracting. So, you know, where you have something like an amplifier that has a gain of 30 dB, that's a factor of 1,000. So instead of multiplying things by 1,000, you're just going to add 30. Anyways, I spoke of that in a previous presentation, so you can review that. We have those on video. Okay, so what do? Well, we have that real device that's adding some amount of noise. You see here I have a signal-to-noise ratio in, a signal-to-noise ratio out. But I'm also adding some noise, N sub A, given below the amplifier in blue text. So you'll see here the signal-noise ratio in and out. So what do? I take the in and I take the multiply by the gain and add the out. Okay, that's how I get that equation there. Okay, back, move forward a little bit. Okay, so again, a perfect device would add no noise. You see here that device is adding just no noise whatsoever, but it's actually increasing the size of the signal. So that would be a perfect device. Again, that's not realistic. So that device would have a linear noise factor of 1, i.e. the input times the output in terms of noise, it's the same, or a noise figure, which is dBs, of 0. In other words, I'm adding no noise to it whatsoever. So here's the standard IEEE definition for noise figure. And you can see here noise factor comes from noise factor. It's N sub A plus KTB. Remember I talked about that before, times the gain over KTB times the gain. So this is really a ratio with the addition of that noise added. So the next thing you're going to find is what happens when I put multiple amplifiers or devices together. How do those work in terms of noise figure and noise factor? And this is what you're typically going to see in a system. You're going to see things that add signal level, so that have gain to increase the signal level so you can process it better, but they're also going to add noise to it. So as you go throughout a chain, you're going to see that the impact of amplifiers or whatever devices as you move further down the chain have less and less impact on the signal, as long as there's gain in front of it. So looking at this, how this basically works, I come in with a noise floor of minus 174 dBm per hertz. Well, there's noise at the output of this amplifier, which is that original minus 174 dBm per hertz, but it's now increased in amplitude by 20 dB. So you see that one minus 174 plus 20 gets me to minus 174. But then I have also some noise added from this amplifier, which is now the 174, but now I'm adding 2 dB to it to get to minus 172. So then if I had a further stage, that again, I have the noise from the input that's further amplified up to another 20 dB, so minus 154 to minus 134. Then I have that same noise added from the previous amplifier, where I'm going to go through this amplifier. So I'm going to take that and then again increase that in gain, and then I'm going to do the same thing with the addition of this noise figure. So these are all going to come together, but this obviously is a fairly arduous process to try and get this added this way. So the way it works is you're going to see I'm going to take the linear terms, and we'll talk about the dB in a minute, which is more realistic, but you basically take the noise figure of the first stage, then the second stage minus 1 over the gain of the stage in front of it. So you'll see here, when you go through the math, as you have gain progressing throughout these cascades, they're going to have less and less impact on the overall noise figure. So you'll see here, I've given a couple of examples, and in fact, you can very easily find cascaded noise figure spreadsheets on the web, and if you play around with these, you'll see how this really works. Okay? So this is a common one you'll see here with a spectrum analyzer. So again, we make spectrum analyzers, and you would think that when I go into a spectrum analyzer that thing is going to be perfect. But in fact, they actually have a noise figure associated with them too. So the newer ones have very low noise figures. They work very well, but they still do have some additional noise, although they can calibrate it out. Okay, so again, we're talking linear terms, but this is really the same thing, but relative to an instrument. Okay, so here's the more general equation. Again, I'm showing you that the noise from each stage, and they're added together. But what do we do? So again, we're in linear terms, so we're using what's called Friss's equation. So it's really, how do I reference all of these things back to the input? So I want to know, what is the noise figure, or noise factor in this case, for linear terms? It's referenced everything to the input of the NN, right, in front of that first amplifier. So the key is I want to know what my system looks like, and that really looks like one amplifier with that given characteristics all conglomerated together. Okay, so when you measure noise figure, and there's actually other ways of doing it, but this is kind of the simplest way that's more traditionally been done, you use a thing called a noise source. So what the noise source does, it actually has a calibrated level of noise. So when you turn it on, you know exactly how much noise it's going to put out, and it's really governed by the characteristics you'll see written on that noise source called the Y factor. And the Y factor really gives you a ratio of what is the noise added from the output with it turned on versus turned off. So what are we doing here? Well, we really want to know is if I have 2 points on a gain curve for an amplifier, obviously an ideal gain of an amplifier would be a straight line with a slope determined by its gain. But if I pick 2 points off of this curve, I can determine what the noise figure added from my device is. Okay, and if you look at a modern analyzer, it's going to do this really all automatically for you. But if you've been around or if you worked in a small company with limited resources, you're going to find that you're going to really want to be able to do this manually. So you take a noise source, look at a spectrum analyzer, probably an older one, and then you calculate these things with a spreadsheet. So in summary, how does this work? Well, first you're going to calibrate it. So you're going to put a noise source out. You want to know what that noise source puts out, right? And you're going to measure it. Okay? It should be governed by the noise characteristics of that noise source, but again, you want to be sure you're taking into account the noise characteristics of the spectrum analyzer. Okay, so you do a calibration step, then you're going to put in your DUT, device under test. So now when I do that, I can take the previous slide and I can now use Friss's equation to determine what that characteristics of that DUT are. Okay, so that's enough on noise figure. So the next thing one might want to consider is, in a receiver, is what we call spurious response. So in a receiver, or when you're looking at reception of a signal, the front end of it typically takes the signal and it's going to move it down to a lower frequency signal. And you're going to find that that's typically done by a thing called a mixer. You'll see that in a couple slides ahead, but that mixer puts out spurs, or things that are unwanted signals, that we need to be aware of. So when we are receiving a signal, we really want to look at the desired input signal and not the stuff generated by the receiver itself or things that are coming from somewhere else that we're not interested in listening to. So one of the key characteristics, particularly dealing with mixers, is the spurious response. So if we look at a mixer, the mixer is typically a 3-terminal device, and there's what we call an RF, an IF, and an LO. So LO, usually you put in a fixed frequency, and it's going to be used to move the frequency from the RF down to an IF, a lower frequency, or from a lower frequency, an IF, up to an RF in the case of a transmitter, which we're going to be just talking about receivers today. So that's all great, but the unfortunate reality is when you do this, you're also going to be generating unwanted signals. So typically, if I take the input for a down converter, so I'm taking a high frequency signal, I'm receiving it to take it down to a lower frequency. So I take my desired signal, I'm going to add the LO to it so that I can get to a lower frequency, and I get the difference. That's typically the desired signal. So for example, if I had a signal at 2 gigahertz and I wanted to get down to 100 megahertz, I'd put in an LO of 1.9 gigahertz, which would get me to 100 megahertz, which is 2 gig minus 1.9, which gets me to 100 megahertz. But the problem is, when you do this, you're going to get all kinds of other signals that are generated. And you'll see a more useful, perhaps, picture of this. But these are all the signals that you get. The signal is the wanted signal. The LO is the tool I use to get it down to lower frequencies. But when I take that, I take signal minus LO, gives me the difference. But I also get the sum. I also get the RF bleeding through. I also get the LO bleeding through. I get 2 times, 3 times, 4 times, all the harmonic terms of all these things, and then integer multiples of these things and differences. So designing a receiver, one of the most challenging parts is actually figuring out all these frequencies and making sure that they don't get in the way when I actually get down to an A to D and I process this signal. And this can be very challenging, particularly in cases where you sometimes actually have more than one mixer, because this can happen multiple times. Okay, so what does this look like? Again, this is sort of a plot of it, looking in the frequency domain. So you'll see here I have an RF kind of in the middle, right, and an LO. So if I want to get down to an IF, which is on the left there, RF minus LO, that's the common thing for receiver. I want to get RF minus LO to get to this IF frequency that I can process, but I get all this extra stuff. So really, you're going to have to design filters around your signal to get rid of these things. But the challenge is to make sure that you don't get a signal that pops up in your filter bandwidth. And that's really one of the challenging things in doing this. And again, you can find lots of spreadsheets and things that help you do this, but you need to be aware of it and figure out all the frequencies. Okay, so the next thing is what we call third-order intercept. So now we've taken a signal at the front end. We've worried about the noise added by that amplifier in the small signal sense, and then we've worried about things from mixers. But another thing is that actually amplifiers generate unwanted signals from larger signals. So, when you, again, look at a amplifier, obviously I want to take a small signal and I want to take that signal and then make it big, right? So I'm multiplying by some number or adding in dB to increase the amplitude of that signal. But the problem is that no device is perfect. So not only are you going to get that wanted signal, so for example, if I had a 1 gigahertz signal and I want to get it from, say, minus 50 dBm to a higher number, I'm now going to increase that, but I'm also going to get some other things that are going to pop up, and you'll see that in a sec. So what this curve is showing is that other products, so other harmonic terms, mix together, and they actually go up at a higher rate. So if the gain of my fundamental frequency is 10, then the gain of my inner mod is 3, and this is a thing, or 30, sorry. So this is a thing you always need to be aware of when designing these receiver systems, and even more so when you do a transmitter. We'll talk about that another day. Okay, so third order intercept, or also called IM3 or TOI, the key thing here is when you put signals that are close together, it makes it very difficult to filter them out. Okay, so when I was talking before with the mixer that you have to design a filter and carefully choose your frequency so that I can get rid of all those terms that I didn't want, well, there's signals that might be close to my carrier which I can't filter out because they're too close. I can't make a filter good enough to do that and still be able to pass my signal. So that's why you need to be concerned about and measure the third order intercept of my amplifier receive chain. Okay, so what does this look like? Well, I take two input tones, F1 and F2. So these are typically fairly closely spaced in frequency, right? I go through the amplifier, and the amplifier's intent is I'm going to put some gain on those. So if I'm coming in perhaps at 0 dBm as a simple number, and it has a gain of 10 dB, then I'd come out at plus 10 dBm. But the problem is I'm also going to get these intermod products. So I get 2 times F2 minus F1 and 2 times F1 minus F2. That's what these two tones are. And you really can't filter them out. They're too close, right? And the closer these two signals get together in frequency, the more challenging it is to get rid of those things. So you need to choose an amplifier with adequate characteristics so that it won't generate noise that you can't process. So this is typically a trade-off. When you go back and look at the noise figure of an amplifier, things that typically have very low noise figure or add very little noise, broadband noise, typically have lower intercept points. So you have to use that cascade analysis to actually determine what amplifiers I put where. And this is really kind of the magic sauce of RF design. Okay? So if you look at the output, again, in the frequency domain, the spectrum of an amplifier, so I have two signals, F1 plus F2, and you get those two TOI terms, 2F1 minus F2, 2F2 minus F1, that are close by. Those I can't really filter out. You're also going to get an F2 minus F1. That's what this guy is here. But typically, in most cases, you'll be able to filter that out. Then you're also going to get higher order terms where these are maybe, like in the case of the 2F1 plus F2, 2F2 plus F1 on the right there with the 3F1, 3F2, those terms are more like a harmonic term, and typically you can filter those out. But again, it depends a lot on your system. When you're designing a complex system, you're going to find that you need to be able to take these things into account and process and put in filters and things adequately. But if you have a broadband system, you're not going to be able to filter these out. For example, like a TV channel, a TV receiver, where you can't filter them out because you need to be able to receive all of those channels from a low frequency to a higher frequency. Okay. Okay, so what does it look like when I measure it? Well, this is showing you an actual amplifier measured with a spectrum analyzer, and you can see I put 2 tones in, and I get the 2 tones out plus the 2 extra terms. Okay? So how do I measure it? Well, I'm going to measure that output level. I'm going to look at what the level is of those output terms, and then I'm going to do some math to determine what they are. Okay? Thought I put that in there, but I didn't. But we'll put that in a note for added on. But basically, you're going to take that delta between the undesired tones and the desired tones, take half of that, and then add it on to the output level. That'll give you what your TOI is. Okay? So when you're looking at the dynamic range of a receiver, so really this is everything all come together where I'm saying I want to know what's the smallest signal I can receive. This, again, could be my cell phone. What's the smallest signal I can receive? I'm far away from the base station, and I can't really hear it very well, so it's a very small signal. I'm worried about the noise figure of my front end, to a very big signal where I'm close to the base station, and it's really big, and I'm going to get these intermod terms or perhaps even harmonic terms. So when you design a system, you're looking at the dynamic range, i.e. the very smallest signal all the way to the biggest signal. Okay? So when I look at an amplifier, what are all the characteristics that I care about? Well, on the left side, the small signal characteristics, there's the KTB. Again, that's just thermal noise. And I want to know what the noise floor of my system is. So, what bandwidth am I operating in? What does that KTB move to dependent on the bandwidth of the system? What's the noise figure of my amplifier? How much additional noise am I putting in from that amplifier? And then again, what's the dynamic range, smallest to the largest signal? The output, you care about the compression because you want things to be linear. So when you put too big a signal in, you get some compression, so the gain starts going down. I care about the output intercept. So again, this is worrying about those terms, the intermod terms that I was just talking about. Adjacent channel power. So that's a case where I have a signal I'm talking on one channel, and there's one next to it, and I don't want it to be interfered to from that. Harmonics, spurious, and then dynamic range, which we already spoke to. Okay, so what does the overall system look like? Well, this is a real simplified case. So I take an antenna. I'm receiving a signal out of the air. I want to take that signal. I want to reduce it to a lower frequency and then amplify it and then go off and listen to it or process it. Okay, so this is oversimplified. We all wish that things were that simple, but they're not. So what does that look like? Well, I'm going to have an RF signal, an LO signal, and I'm going to get an audio signal here. So you're going to get an image, which is basically a copy of that RF that will show up. This is, again, an undesired signal. But I can put a filter around that audio signal to the left so I can knock out all this other stuff. So that's a fairly easy problem usually to deal with. But in the real world, there's going to be more complexity to these things. So if you look at it, there's that same sort of stuff on the left, but now I have an RF filter added to it. That's to first off limit the bandwidth of my spectrum so I know what the noise bandwidth I'm working in. But it's also to reject other signals coming from other things, cell phones, cars, garage door openers that I don't want. That comes to a lower frequency, which we call an IF. Then that IF signal is filtered again, and then it's going to be further reduced to a lower frequency and then processed. So in the old world, things were just audio, but obviously this would be something more like data today. Okay, so what do these frequencies look like? Again, this is a similar analysis, except now I'm moving twice. Okay, so I take a signal, I move it down to an IF, I'm going to get the RF, I'm going to get the LO, and then I have to filter these things out. Okay, and here's basically showing you what some of these terms are that I have to worry about, and I'm not going to go through these in great detail because I think hopefully the analysis makes sense now, but these are all the terms that I have to worry about. And there are mixing products that go up into many higher level integers. I'm showing 3 and 5, but depending on what you're trying to do, you may have to be concerned with those other signals. Okay, so when you put all these things together, you have to do what we call a cascade. So really what the cascade is doing is trying to reduce everything all as separate entities, like separate amplifiers and mixers, and then moving them all to look like one device. So what is the overall intermod product? What is the overall noise figure? What is the overall gain of my system? So we have, again, tools for doing that, but you need to be aware of what's going on. Okay, so when we look at the overall characteristics, again, these are all things I've talked about. What's the noise for the system? What's the noise figure? Spurious, again, from mixers, harmonics, third order intercept, LO, RF, and IF. Isolation, that's really things bleeding from one port to another. And then looking at those things all being reduced to one single device. So if you were to look at what an overall system looks like, we've been talking about receivers. So in this overall block diagram, this comes from one of the books I'll mention in a sec, but the overall top part of this is the receiver, but typically in a thing like a cell phone or whatever, you're going to find that there's an accompanying transmitter section in that cell phone, which also operates. Okay, and they also need to not interfere with each other and bother each other. So again, I work for Rohde & Schwarz, so what do? Well, when we design all these things, we need to make sure each piece of it works. So not only does the amplifier work, the mixer work, the filter work, do they work in unison when you put them together in a cascade? Do they behave in a manner that you think is predictable based on the equations and things that we've talked about? So you typically want to use some of these tools to measure these things. Okay, so a common one, I think probably most people who are familiar with technology are familiar with, is an oscope. It's really one of the more basic instruments. Typically, if you did electrical engineering or if you did something like technician school, you probably have seen one. Gives you voltage time, frequency, rise time, things like that, and you can look for distortions too. Okay, and Rohde & Schwarz makes those, and they're very nice, very user-friendly, and very powerful. Spectrum analyzer, this is again more in my world. So I'm looking at frequency versus amplitude, but I can measure other things, group delay, phase noise, noise figure, complex modulated signals like things in cell phones or wireless LAN. We have the ability to process some of those signals. Okay, another thing, signal generator, it really acts like a transmitter. It generates all of these signals and then some and gives you the ability to emulate, if you're receiving something transmitting to you in some format that's predefined and predictable. Okay, vector network analyzer, this is kind of one of the things I work with. It gives you the ability to measure very precisely characteristics of things like an amplifier, what we call an S parameter, to look at what's the phase and amplitude characteristics of that device and how it's going to affect your system when you put it in it. Okay, power meter measures power. Seems obvious, but it's kind of one of the first devices that you start out with when you build a system. Okay, so in conclusion, RF system design is a complex process. We've talked about some stuff before. These are some of the characteristics that you need to be concerned about. What is the environment I'm working in? How big, how small, how much power? Is it handheld? What information am I sending? Is it data? Is it voice? Is it video? Things like that. How much bandwidth do I need? Am I sending stuff two ways, like a cell phone? Am I sending stuff one way, like a TV set? Are things moving or stationary? Things are moving, you get other things that you need to be concerned with, like Doppler shift, where basically the frequency is changing as a function of the velocity you're moving at. And what's the cost? Obviously, in today's world, people like cheap handheld things, so price is obviously always a primary concern. Okay, here's two really good reference books. RF Design Guide, I've used this a lot in my career, by Vismuller. I think it's still available. And then on the left, Practical RF Design. This gets a little more complex analysis. I actually worked with this gentleman when I worked at TRW. He's passed away now, but really great guy, very knowledgeable. And that's all I have. And if there's any questions, let's go ahead and take those.
Great, thanks so much, Neil. Let me just share my screen now, and we'll get to any questions that came in. We did have quite a few coming in. Let's see. So to begin with, we have, what is the difference between analog and digital modulation?
Okay, hopefully you can hear me okay?
Yep, we can hear you.
Yeah, thanks. So the primary thing really is, what is the information that you're trying to transmit? So obviously in today's world, working with a computer, modem, even television signals now, really, the information that you're sending is digital. So the simplest answer to that is really that I'm sending digital information, so it's easier to process everything remaining digital. But in actuality, a lot of why things have gone so digital is in the cell phone world, the requirement for increased capacity has really driven a lot of these technologies. You see all the complex modulation schemes really come initially from the cell phone world, so that they can use every little piece of spectrum that they can as close to all the time as possible, because they paid a lot of money for it and they want to get a good return on their investment.
Great. Another question we had was actually kind of along those lines. Why do they use digital modulation?
Yeah, so really it's about spectral efficiency. So, you know, the spectrum, electromagnetic spectrum, I don't remember if I showed that graph, but, you know, typically governing agencies like the FCC define who gets what piece of spectrum, and it's a limited resource. So, you know, the military has some, the cell phone companies have some. So a lot of what they're trying to do is be able to use every hertz of bandwidth more efficiently, so that they get more information on it and be able to reuse it as much as possible.
Great. So I see actually we're reaching the end of our time. If you guys have any more questions, then we will be getting back to them. We have one that's a little bit more complex, so I think maybe we'll take that one offline.
Okay.
But if you have any more questions, please go ahead and type them into the Q&A section right now. And in the next couple of minutes that we still are here, you'll be able to answer them.
Okay.
Oh, someone would like to see the 2 books at the end. So actually we can send you those books via email, the titles of those after the webinar, so you have those saved for yourself. Okay, great. So thank you everyone for joining in today. If you do have any more questions, or you know, for Neil or for anyone at TestForce, then you can definitely send us an email straight to webinar@testforce.com, and we'll get back to you. And you can also look for a recording of this webinar in your inbox within the next couple of days, so that you can rewatch it or share it with anyone you'd like to.